Hello, my name is Alexander Lee, and today I will be doing a presentation on Peyote Pharmacodynamics. So before we get into my main topic, since this presentation is geared towards a more general audience, I want to go over some background information related to how your nerves talk to each other and what those specific chemicals do to one another, to the different cells in your body. So neurotransmitters are chemicals that neurons release in order to send signals to one another. Their effects on other cells depend on their chemical structure and what type of cell is on the receiving end of said signal. For example, glutamate is an excitatory neurotransmitter, meaning that it promotes the creation of an action potential. Glutamate is right here. In opposition to that, GABA, or gamma aminobutyric acid, is an inhibitory neurotransmitter, meaning that it inhibits the creation of an action potential. Their functions can go even further, with glutamate being an important neurotransmitter in learning and memory, and low GABA levels being linked to generalized anxiety and other psychiatric disorders. Glutamate depicted right here and GABA depicted right here. Neurotransmitters normally attach to the receiving cell via a receptor. Some chemicals, when in the body, attach to these receptors by imitating the structure of a neurotransmitter and have an effect on the receiving cell. These are separated into two categories based on what the receiving cell does in response to it attaching. Agonists are like super neurotransmitters, making whatever the receiving cell was going to do when the neurotransmitter bonded to it happen at a greater volume or frequency. Antagonists, on the other hand, completely stop whatever activity the receiving cell would have performed if the neurotransmitter had attached at the site. You can see right here, this is an example of just a normal neurotransmitter attaching to a receptor and normal cell activity, whereas with an agonist, it too has a similar shape to the neurotransmitter and can bond to the receptor. And when it does bond, it causes the receiving cell to have enhanced cellular activity. Whereas with antagonist drug in this case, it also has a similar enough shape that it can bind and bond to the receptor and prevent other neurotransmitters from coming in and attaching there, and also prevents whatever cell activity was going to go on from happening. All right, with that out of the way, we can get to my main topic for today, peyotes, specifically the chemical in them, mescaline. So peyote and mescaline. The peyote is a small cactus found in South Texas and parts of North Mexico, shown here on the right. Native Americans have been using the slices of a cactus for more than 5,000 years as a hallucinogen. But in the 1960s, it was classified as a Schedule I drug and therefore illegal in any capacity in the United States. But a special exemption has been made for traditional ceremonies. The main psychoactive chemical in peyote is mescaline, of which its structure and function I will be covering today. This right here is mescaline. You can see that it has a couple key features which make it similar to other neurotransmitters. Mescaline is a substituted phenylethylamine, meaning that it has this ring group right here called a phenyl, two carbon atoms branching off from the ring, this carbon and this carbon right here, emphasized as bens, which is the ethyl. And finally, this nitrogen-hydrogen group over here, nitrogen, two hydrogens, called an amine, phenylethylamine. This pattern of a ring, two carbons, and nitrogen is a key characteristic of mescaline because, as the saying goes, structure determines function. It can imitate the functions of different neurotransmitters, mainly noradrenaline, dopamine, and serotonin. All three of these have a similar enough structure in the phenylethylamine. Phenylethylamine. This isn't the same phenyl, but it's a ring structure, ethyl and amine. It can imitate the functions of these different neurotransmitters in the central nervous system due to this characteristic chemical structure. Mescaline attaches to the 5-HRT2A serotonin receptor in the central nervous system and acts as a partial agonist to activating. Partial in this case means that when compared to how active a neurotransmitter would make the cell when bound to the receptor, mescaline only partially activates, leading to a smaller response. Due to its similar structure to dopamine, it also interacts with dopamine receptors, but it is unclear if it acts as an agonist to dopamine itself or the dopamine receptors, or initiates the release of dopamine itself. Currently, the mechanism behind why mescaline produces psychedelia is unknown, but has to do with the excitation of neurons in the prefrontal cortex. The psychedelia it produces is similar to other psychoactive compounds, such as LSD and psilocybin, but distinct in producing geometrization of three-dimensional objects, where they appear as cubist paintings. Another interesting difference is that the visual effects from a mescaline trip are best experienced in low light conditions with one's eyes closed. This right here is the receptor, and it is still currently unknown how exactly it produces the psychedelic effects, and that could be a topic for further research. So there we go. That is the end of my presentation. Right here are all my works cited. I hope you learned something new from this presentation, and if you have any comments or any, piece of advice, I'd be welcome to hear it. Thank you.